Morning. Thank you for coming. My pleasure to welcome you to this talk by Yasaman Ghasempour. She's completing, or nearly completing her PhD at Rice University on an area which is admittedly one of the emerging threads within 5G networks. As you see on the slide, she's going to talk about her work in millimeter wave communications. Her work consists of contributions to both what we call high density, high throughput networking scenarios, mostly both for indoors and also for outdoors. Besides the high density aspect, she's worked on cross-layer aspects that contribute via sensing to improved millimeter wave networking. So today her talk will reflect a mix of both comms as well as the networking necessary to enable such comms efficiently. Amongst her credits, she's had a paper, she's a finalist, I guess, at WinTech. She holds a TI fellowship. And without further ado,
Thank you so much. Can everyone hear me? I think I'm good.
Do you need this?
No, do I have one? Okay. Thanks for the introduction. I'm so excited to be here and talk about sensing-assisted millimeter wave networks for dense high-rate applications. Today's wireless applications and use cases have evolved significantly. The appearance of radically new data-hungry applications, such as VR and AR, demand for gigabit per second scale data rate that is order of magnitude beyond what today's LTE and Wi-Fi can support. That's why today millimeter wave technology is emerging. Millimeter wave bands spanning from 30 to 300 gigahertz can give us a lot of available spectrum that in communication language can translate to potential for high data rate. In the 60 gigahertz band alone, we have 14 gigahertz unlicensed bandwidths. This means that using this new frequency band, we can potentially now offer this gigabit per second scale data rates. But there is no free lunch. As we move up in frequencies, the path loss and the scattering loss will be much higher. In the 60 gigahertz bands, we have 20 to 40 dB higher propagation loss comparing to a sub-6 gigahertz band. It means that to establish a link, we need to focus our energy into one specific direction, meaning directional communication. Fortunately, in these bands, we have millimeter scale antennas, allowing that we can now pack many more antennas into the same form factor. I'm showing a 24-element antenna array that is just as size of a quarter coin. Using these antenna arrays, we can now form directional beams. So the first IEEE standard for directional wireless is out. It's called IEEE 802.11ad, which gives us peak rates up to 6.7 gigabit per second. And it enables directional transmission and reception. And basically, it has a predefined set of directions, or what we call beam, to search from. So basically, establishing a directional link has two phases in 11ad. Which basically in the first phase, access point sweep through all of its directional beam, sending a packet, the client on the other side basically receiving this packet in an omnidirectional mode, analyzing the SNR of such packets and find which beam gives us the highest signal strength at the access point side. The second phase, it's now client who is sweeping, again doing the same procedure, while access point is receiving and finding the best beam at the client side. Then they can now exchange basically feedback and then log into their basically best direction to communicate to each other. So from now on, they can now send and receive directionally. So in such directional wireless, sensing the device and also the environment can help us a lot. Let me give you two examples. For example, if we have the client tell the access point it's XYZ, then the access point can just automatically actually steer toward that specific XYZ and can basically remove the time needed for searching through all possible directions. Or for example, if the access point and if the link between access point and client, the line of sight link is blocked, and there's a reflector nearby, they can actually, with the knowledge of reflector, can steer toward that reflector without the need to scan over all possible directions again. However, However, there are two key bottlenecks that I'm trying to solve with sensing, and I'm going to talk about that in this talk. The first bottleneck is mobility. So when we have our basically aligned beam, a small rotation or translational motion of the device can cause beam misalignment and eventually link outage, which basically means your gigabit per second scale data rate can drop to 0 really quickly. The second one is that scaling to the high dense population in the terms of clients, we have still this limitation of serving one client at a time. Even though we have so many resources and the access point, we still can send basically one directional stream at a time. And I will talk later in this presentation why it's challenging to actually do multi-stream communication. And it's basically because of the interference, and actually canceling those interference is challenging. So with sensing, I'm going to address these two bottlenecks. So here's the outline of my talk. First, I talk about sensing-assisted mobility management, and then sensing-assisted inter-user interference management. At the end, I conclude with my future directions. As I just mentioned, the mobility can cause beam misalignment. To recover from that, we have to again go through all this scanning, which we call beam training. So if we don't have mobility, or in semi-static scenario, we can actually do this beam training once and use the beams at both ends for multiple consecutive data transmission. Whereas in mobile cases, we have to sort of retrain frequently before every packet transmission. It means that this frequent retraining and the overhead associated to it can actually make the throughput be much smaller than the physical rate, which, for example, for 11AD was 6.7 gigabit per second. Then we ask this question that, can we eliminate this retraining overhead? And the answer is yes, but there is a big if here, and the if is if we can actually track the line of sight angle between the access point and mobile device, we can eliminate that. We can just steer to the current location or position of the mobile device. So the idea is to sense and track the line of sight angle using light. Why light? There are three main reasons. The first is if we do this, handle this kind of sensing in out of millimeter wave band, then there will be no interference from this sensing back to our communication. So we can actually run this in the background, sense this for multiple clients at the same time without interfering with any sort of potential communication in the environment. The second is light propagation is line of sight dominant, similar to millimeter wave. And finally, we already know a lot about line of sight light, how it propagates, and we have an analytical model that has been shown to be close to the basically experimental result that we can actually use in this setup. So we designed and implemented a system called LightSteer. LightSteer is the first light-controlled radio system, and it uses light sources as fixed line of sight anchor to track basically the device motion. And to sense the light, we put photodiodes on the mobile device to sense that light. And as the device moves, the current in this photodiode is going to change, and that's how we can infer motion. Specifically, we actually repurpose the access point's indicator light, which you can see. Basically, in that special case, then the line of sight that we get from light directly maps to the line of sight angle in the millimeter wave band, because millimeter wave modules and light source are co-located. So LightSteer overview is as follows. There's this initial basically lock-on, which happens after that scan over all possible directions or beam training. And as the device moves, you can see beam is going to be misaligned, but this difference is detected by photodiodes, and the beam is automatically adapted. For this to work, we need to sense and track the 3D angle really fast. So how are we going to do that? Let's look at the model, basically the intensity at a specific photodiode from a light source. It's depends on three main factors: the angle of arrival, which we're looking for, the irradiance angle, and the source sensor distance. There's this constant value which depends on the transmit power, the area of the photodiodes, and also the receive gain, which is fixed, and it can be basically known by calibration. You can see that this light intensity I depends on three unknown variables. So with one light intensity measurement, we cannot solve for these three unknown variables. And also we cannot rely on the phase information here because light is incoherent. So we put, to solve this challenge, we put an array of photodiodes with known geometry on the device. For example, we can now put 6 of them on each edge of the device. And if we assume that the distance from light source to the device is much smaller than the device dimension, then that irradiance angle and also distance is almost similar for all these basically photodiodes. The only thing that is different is the angle of arrival. So we can estimate the 3D angle using sensors in 3 perpendicular planes. I'm not going to show you the equation, but it's easy to solve. So we actually built the first prototype of light steer. You can see in the light side, we have these light sensor arrays, which are like a custom array. It's like as big as like your tablet or a big smartphone. And it has 6 lux sensors. They're all being bought off the shelf. They are really cheap, few boxes. And on the millimeter wave side, you can see we have UBIC transceiver connected to horn antennas. One of the antennas is actually co-located with a light sensor, and the other one is over here. And we connect that to the warp baseband, and basically the overall system operates at 60 gigahertz on license band.
Question?
Sure.
Are there assumptions about ambient lighting or stuff that you have to take care of? Could you comment on that?
Sure. There is a lot of prior work trying to use some modulation on the light itself that has been done for VLC communication. So here, basically, LightSteer can adopt all those techniques to differentiate that the LED indicator from any ambient light.
So you only need to take care of the dynamic range in the very front end?
Yeah. Okay, the first question is how accurately can LightSteer estimate that angle that we were looking for, comparing to the ground truth. So we did the overlay experiment with different configurations of the client access point being co-located with the light source. And I'm showing the distribution of angle estimation error in all different orientation and location that we tested in an indoor environment. And you can see that error is within 2.5 degrees for more than 75% of our measurement instances. And if we want to translate this to the beam selection problem, with 7-degree beam, we are either selecting the right beam, which gives us the highest signal strength, or we are off by 1 beam, which is pretty good. But how does that translate to throughput? How we are basically boosting the throughput? Here, to evaluate that, we are reclaiming the airtime overhead that we saved by this like sensing for data transmission. And we are considering a typical scenario, indoor environment, the clients are moving at walking speed. And we found the throughput versus number of clients. It's normalized to an Oracle scheme, which always knows the optimal beam configuration and always do the best job in terms of modulation and coding selection. So basically, that's the upper bound. That's the best we can do, and we normalize toward that. And you can see that with only 10 clients, we can get 2x gain versus baseline 1180. As you have more clients, basically, you spend more time on the training. 1180 does that, and also there will be contention from the client competing to get access to the channel so that they can now train and find the right beam alignment. That's why, as you have more clients, you have see baseline scheme do great. Okay. This was how we can handle basically mobility using sensors. But let's move on to a more complex problem when our goal is to scale to dense user populations. Here we want the access points to simultaneously transmit to multiple clients using the same frequency band and at the same time. Meaning that the access points now wants to send like a YouTube video to one user and a Netflix video to another user. That's why it's independent data. You may think that's an easy problem to solve because it's directional. I can just send one stream in this direction and send another in this direction, and they are blind to each other. Well, that can be the case if we have sort of laser beams, meaning if the beams are pencil-shaped and narrow. In that case, I am showing here, for example, the interference can be 0 as long as you have sufficient angular separation at the client. You are good to go. But in real world, beams actually are imperfect. And the reason for that is, goes back to the node architecture of millimeter waves. We can have, as I mentioned earlier, we can have many antennas in the device, access points, and clients, but we cannot have that many RF chains. RF chains has power-hungry components like ADCs that we cannot afford to have that many of them in access points or our devices. So we end up in a situation that number of RF chains is much smaller than the number of antennas in the system. So the way to actually generate directional beam in such system is through phase shifters, meaning that you have only control over the phase of the antennas. You apply different phase delay to actually generate the beams. And you have also limited resolution at the phase shifter itself, which all of these together end up having these irregular beam patterns. These are all measured beam patterns from this 24-element antenna array which I showed earlier. You can see we have strong side lobes, we have overlap, so we will see a lot of interference. But that's not the only problem. Actually, mitigating interference incurs overhead. We cannot do it in the digital domain because of the higher pass loss and because of the overhead associated to it to get the channel for every antenna at the transmitter to every antenna at the receiver. So we have to do it in the analog domain. And for that, under fixed beam configuration, we need to send two channel sounding packets and wait for the feedbacks. That's the amount of overhead we need for this fixed beam configuration to test, just to measure the interference for this beam configuration. But there are a lot of beam configuration to test. Actually, for S streams or S users, we have order of n to the power of S different beam configuration to test. And that means hundreds of millisecond airtime overhead. Then we ask this question that, can we narrow down the beam search space? And we intuitively should, because the beams that do not provide high SNR for a single user communication, they are probably not a good option for multi-user communication when there's interference too. So in our baseline scheme, we consider only beams that provide high SNR at every client. But I'm showing you later that this doesn't work in real systems. And we need a more sophisticated, smarter way of selecting beams. We know that millimeter wave channels are sparse, meaning that only line of sight and first order non-line of sight paths can exist in real channels. In most of the scenarios. So if we can actually sense these few spatial paths or directions, we can ideally predict the interference without the need to do over-the-air transmissions. Let me give you an example. Let's say we use these blue beam patterns to actually serve this client number 1, and we want to understand or predict the impact or interference that this beam is going to cause on this user number 2. If we have this dominant path, line of sight and reflected path from the access point to user 2, and we also have the radiation pattern of this beam, we can predict the interference. It's just the radiation, it's the directivity gain along this dominant path. Knowing the radiation pattern is not a big deal. Actually, radiation pattern is just the basically deterministic function of the array geometry and the codebook that we put, and they are all known and fixed a priori. But finding and sensing this path, especially the reflected path, can be really challenging. And to think about that is basically when we are sensing the reflected path, we want to find some information about the relative position of reflectors with respect to the access points and the client in the environment. We know that windows or like metal surfaces can be good reflectors, but when we enter an unknown basically environment, how can we find the relative position angle from these reflectors? So we designed a system called MUTE to do so. MUTE stands for Multi-Stream Beam Training for Millimeter Wave Networks. It's the first path sensing platform in millimeter wave, and it uses limited in-band measurements to do so. Why we need measurements to be in millimeter wave? Because reflection from one frequency band does not directly map or translate to another frequency band. So we want these measurements to be in the millimeter wave band itself. But which measurement? Because these measurements can themselves actually cause extra overhead to the system. We are repurposing this link acquisition beam sweep, which I explained at the beginning of the talk, to do so. That happens every 100 milliseconds in 11AD and 11AY SN dot, and by just repurposing that, we don't basically incur any extra overhead to sense and measure this path. So if you remember, those initial beam sweeps in each of the phases, one side was directional, another side was in omnidirectional mode. Let's say access point is directional and use this directional beam pattern. If we now, instead of looking at the SNR, look at the channel that the client sees, it should look like something like this, because it captures two paths, a line of sight and a non-line of sight. And because the lengths of these paths are different, we expect the delay or arrival time to be different. Also, the amplitude of the peak or the amplitude of the channel depends on directivity gain along that path. So if we want to model the directional channel in that case, it's a function of radiation pattern, and also the peak depends on the path length. In millimeter wave system, we have gigahertz scale sampling ring, which was not available in lower band. So we can now distinguish and detect this different path with centimeter scale path length resolution. In this testbed that I'm using with 2 gigahertz wide channel, we can actually distinguish between two paths that have 17 centimeter or higher path lengths different, which is pretty amazing if you want to compare this with lower band scenarios, which we didn't have this capability. But this was measurement for one specific beam only. But we have measurements across different beams, and we can compare them. If we compare across different beams, we expect to see actually one path being captured by multiple beam patterns, because channel is sparse and beams have so much irregularity and overlap that you expect to see those scenarios. But if you have multiple beams capturing one path, the physical channel, the physical wireless channel does not change basically, meaning that you still have the same physical path, they have the same physical path to the client, but just applying different beams, you are changing the directivity gain or strange over those certain paths, meaning that these beam patterns are just acting as an amplifier, amplify your strengths along certain paths. It doesn't change anything in the physical side of the channel. Meaning that if we compare, let's say, these two beam patterns, both capturing P1 and P2, we should see, and we see it in over the experiments, that they have peaks at the same time, but with different actually amplitude, because, for example, the pink beam pattern has higher directivity along the non-line of sight, so the amplitude of P2 is higher for that channel. So with these two key observations, we can now form an L2 norm optimization framework, try to find the angle that minimizes the difference between the measured channel and the channel model that I described over all different beams that we test. So to give you a clear example, let's consider this. So we have this beam pattern, and we know that the channel is corresponding to this beam pattern looks like this. There's a peak as 25 nanosecond, and we want to find the angle corresponding to this path. We know that we know the radiation pattern, so we can calculate the average directivity for that beam pattern. And having that path or having that peak tells us that this path should fall into high directivity region of this beam pattern with higher likelihood or probability. Meaning that if we had only this measurement, this beam pattern and this measurement, we would have kind of expected to see this path kind of falling into those areas that I show here, right? Let's have the second measurement. Let's assume in this toy example that this second beam pattern actually has one completely overlapping lobe and one completely different lobe. And we exactly see the same peak at the same time, but with different amplitude. Having these two together, now we can say that there is higher likelihood for the path angle to be in the overlapping area of these beam patterns. So what I'm trying to say that by just two measurements, we can now narrow down the basically interval that this path may fall into. And you can imagine that having all these different radiation patterns in our codebook, we can actually now, with fine resolution, better resolution, find the path angle. So this is basically, this was one example to find the angle corresponding to one path for one user. But we can do the same, extending to all the paths to all the users. So if I want to summarize mute, we use these mandatory beam sweeps and the radiation pattern knowledge to sense the path. For sensing, we actually leverage key components of millimeter wave systems, which was channel sparsity, gigahertz scale sampling rate, and irregular beam patterns. Then, now having this path information, we can predict the interference and form beams that have minimum interference. I'm not going to go to the details of that. Just going to give you one example. If I have two clients and one reflector in the environment, the SNR-based scheme gonna kind of maximize the SNR toward the intended client and doesn't care for the interference. So it ends up actually choosing beams that has highest directivity along the line of sight path, which is the strongest path. But if mute tells me that we have a reflected path and we can steer one of the beams toward that reflected path and potentially reduce the interference, we can actually get a better sum rate and throughput performance. That's the comparing between basically mute and SNR based. So we implemented mute. We used National Instrument transceiver, a psi beam up converter, and 24-element phased array that has 2-bit phase shifters. So the sampling rate, as you can see, is 3 gigasamples per second and 2 gigahertz wide channels. We have 60 gigahertz band operation, and then we have programmability over phi and Mach. Using that, we actually implemented key components of mute for measuring and basically sensing the path. The user-defined beam sweep, for example, the channel measurement during sweeps, detecting the peaks in the channel, angle estimation, and also at the end, trace-driven multi-stream over the air data transmissions. So this was the first experimental exploration of millimeter wave multi-stream communication. We tried different environments, typical environments, indoor. For example, 2 different configurations at lobby, typical office cubicles, conference room, corridor, and I'm not going to go over all the details of that, but I'm going to show you one result, that how actually mute performs comparing to the baseline and also exhaustive search. Exhaustive search basically tests all beam combinations and find the one that gives us the highest sum rate. Of course, this is not practical in terms of the overhead, but this actually gives us the upper bound of the performance. So that's why we are interested in looking and comparing mute with exhaustive search. And that's how basically the figure looks like. So I'm showing the aggregate phi rate over the y-axis and number of spatial streams over the x-axis. You can see that mute closely follows exhaustive search, even with higher spatial streams, like for example 6, whereas baseline actually does not scale with number of streams. The reason is that as we have more streams, we have potentially more interference in the environment, but SNR-based scheme just tries to maximize the SNR, it doesn't account for the interference. And so this is the aggregate phi rate. If I want to include the overhead, then the baseline and mu would actually both kind of win over exhaustive search because of the overhead that exhaustive search needed. So throughout this talk, up to now, I talked how sensing can help and enhance millimeter wave communication. And I gave you two examples. First, how we can sense device motion to actually manage and handle mobility, and how we can sense a sparse path in the millimeter wave to actually handle the interference and consequently basically enable multi-stream high-rate communications. In future, I am interested in looking into communication-assisted sensing aspects. The motivation is that we will be kind of surrounded by millimeter wave devices and signals in the future. And if you think about it, all of the smartphones' access points are going to have tens to hundreds of antennas in them that are purposed for communication. And also, we're going to have a dense deployment of access points because of the limited range that we have in millimeter wave. So if we can repurpose this communication-dedicated hardware for indoor millimeter wave sensing, that can give us a great resolution because of the high bandwidth and millimeter scale wavelength. So we would ideally be able to sense a millimeter scale motion using this communication-dedicated hardware. And it can have countless applications, for example, from like larger scale motion detection like fall detection all the way toward like health monitoring or vital sign detection because ideally, again, we can sense millimeter scale motion. And you can think about this is a challenging problem because we want to single out a millimeter scale motion from a large amount of mobility and motion in the environment. Also, I am excited to actually kind of go outdoor and use this millimeter wave module for both sensing and communication, integrating it with drones or UAVs. So if we put these millimeter wave modules on the drone, that can be really helpful in both communication and sensing aspects. In the communication, we can now have high-speed links to a ground unit, potentially to offload a large amount of raw sensor data and let the ground unit actually handle that. And we can have high-speed links to the other drones and then have like distributed sensing missions in that sense. In the sensing part itself, we can now have missions like target tracking, environment sensing, so we can potentially now sense if there's a building here and change the route or make sure we're not kind of colliding with that building. Also, we can detect pedestrians if they are, for example, carrying a mobile device, and there's like a periodic sweep. So by just finding the angle coming from that signal, we can now make sure that the drone does not kind of hit a pedestrian walking nearby. So there's a lot of kind of design space and potential applications here. However, when we go outdoor, the sort of challenges that we see different is in a scale. First of all, we have higher range, so the SNR is lower, and we have to deal with basically low SNR sensing and processing, and then also the scale of mobility is higher than walking speed. So we have to have like efficient way of tracking that mobility and beam steering, 3D beam steering. And the end, these drones actually they have limitations on power consumption, processing resources, so we cannot, for example, run really heavy signal processing techniques on that on them, and we are having limitations on that too. So here's the list of publications. I encourage you to go and read them. I'll talk about a lot of them here. And I want to actually acknowledge my collaborators at Rice, Dr. Knightley, my advisor, my former colleague, Dr. Haidar, at Intel, Dr. Cordero, Professor Kosto-Nicolas at University of Buffalo, and Dr. Middleman at Brown University. So to summarize, I talked about how we need directional communication in millimeter wave bands and what are the key bottlenecks, mobility, and scaling to dense user populations. For the first bottleneck, I introduced light steer, which tries to steer the beams by sensing basically device's motion. And on the second bottleneck, I introduced mute, which actually sends path, reflected path, and line of sight path to manage interstream interference. And in future, I would like to actually repurpose the deployment of millimeter wave access point and devices for joint sensing and communication applications. And thank you. I'll be happy to take questions.
Questions?
So I have a question on the light steering. So the assumption is that the training using light will happen faster than the training using just the millimeter waves.
The assumption is...
What's the base of that?
Good question. The assumption is that it can kind of be passively sensing in the background the motions, and then you may not need to actually send data to the device all the time. But when you have like downlink data to send the device, then don't need to find the current position. You already know it because it's kind of running in the background.
So it's a keep calculating orientation. So another question, at least in your cell phone, you have a accelerometer, you have a MEMS, in the future, gyroscope. So you pretty much can predict the motion, the rotation, the orientation of the phone. Can you use that information to sort of predict the orientation, so preempt the misalignment of the beams?
Yeah, potentially, yeah. But it should be basically the scale of error that we have using, let's say, for example, GPS for finding a location. It's like it's like in the order of meter scale, which is like, we need basically to find tracking of the device so that we can actually steer toward that. So I think in future, as these devices get better accuracy, potentially we can do that. If also we can somehow reliably and in a fast way feedback this information that is local on the device to the access point. That's also a potential that we can look into in the future.
How do you deal with the difference in transmission and reflection of light compared to the transmission and reflection of the millimeter wave? So you could imagine a situation just, well, a cell phone in the pocket, for example, should have good millimeter wave connection, but not any light connection. Or you have a window or a mirror that's a great reflector for light and not a reflector at all for the millimeter wave. It seems like that non-ideal situation. Is there anything to deal with that?
Yeah, there are some limitations when using light. That's a great question. In light, we can actually track only the line of sight. And we cannot actually track that much the reflected path because, as you mentioned, it's not reliable. You cannot directly map a reflected path that has been sensed in light and map it to the millimeter wave band. So in those scenarios, when let's say the line of sight path is blocked, it's in our pocket, then light steer will basically fall into the traditional 11AD way of finding the right beam. But when line of sight path exists, it can sense it and track it. Just at the right.
Or what if there's a window that is a good reflector of light but not a millimeter wave, so the light thinks that's a
Yeah,
light
so,
is saying yes and the millimeter wave is no.
Yeah, so that can happen certainly, and we've seen in our experiments that if the reflector is close to the device position, so the receiver is actually line of sight and non-line of sight angle is really close, then you can get errors in your measurements. But in overall, basically, the amount of error that you get is within the beam width of the millimeter wave, because millimeter wave, as I showed in practical scenarios, the beams are pretty wide. Right? So even if you basically mistakenly found the non-line of sight, which is like a few degrees away from your line of sight path, you still be able to find a beam that can basically give you high signal strength because the beams are wide.
Somehow there's a conflicting argument here because the millimeter wave you are using line of sight. At the same time, you want to get facilitation through the light, which is also line of sight, and end up with as long as you cannot get the line of sight, and then both of them possibly will fail. At the same time, when people using like Wi-Fi, traditional Wi-Fi for the polarization, I don't have to worry about line of sight. Then I can facilitate the millimeter wave transmission using the existing like a Wi-Fi type of the localization. So why did you choose the light as your steering or localization mechanism, which also prevent yourself from the night side issue?
So we looked in this problem in other bands too, in 2.4 and 5 gigahertz band too. And basically the motivation there was that you already have these chipsets, for example, Intel chipsets that have 2.45 gigahertz and 60 gigahertz modules in it. So you can use 5 gigahertz or 2.4 gigahertz for line of sight sensing. But again, the conclusion there was that you cannot map the non-line of sight path because there's a huge difference between the reflections you can get in 5 gigahertz and 60 gigahertz. And if you think about it, it's just mostly because of the scattering loss that is much higher at 60 gigahertz. So I can have a reflector, for example, over this wall at 5 gigahertz that cannot be sensed in 60 gigahertz, right? And then again, as you're comparing 60 gigahertz to light, which is like much higher in frequency, you have the same problem. If I sense like a reflector in light, the light scattering propagation characteristics is different from 60 gigahertz or millimeter wave. That's why we were not looking for inferring non-line of sight path using light or 2.4 and 5 gigahertz. But the main idea was if we can track the line of sight and line of sight exists, then we can handle mobility. But for multi-stream communication, we would ideally need more because of handling interference. If you always sense the line of sight, let's say with LISD, right, and try to handle multi-stream communication, you will be basically doing as good as SNR-based scheme, which was the baseline scheme, because that's what you need for SNR. You know the line of sight angle, and you just select the beam that has highest directivity along the line of sight path. That's why reflection can actually give you that boost that you see the gap between SNR-based and mute.
So I have a couple of questions. So basically, it sounds like you described two different approaches to sort of for beam acquisition and finding the highest throughput path for a beam. In the first approach that uses light and LiDAR, I mean, one thing I would argue is how practical is that, right? Because at the end of the day, these are targeting consumer applications and mass deployment. I would think that that would enhance the cost significantly of having that extra hardware associated with, on top of the phased array itself, the radio itself, the communication channel. And then in the second approach, I'm kind of wondering in an outdoor environment. So if I have a base station, and if you want to apply it like to future work, to track drones and communication with drones, isn't an outdoor environment considerably more dynamic compared to an indoor environment? It depends on weather, wind, moving objects around. And so it seems like applying this technique would be more difficult. I may be wrong, basically because you're going from a stationary indoor environment to really a much more dynamic outdoor environment.
Okay, yeah, great question. So on the first question, I agree that you need to change basically the LED indicator on the access point. I am not sure about how much would that cost, but basically you need to just replace it with an LED that has some sort of modulation on top so that you can detect it. I don't think that would be I assume that with replacing all these access points will be a huge infrastructure cost, but if at the end of the day you want to move into millimeter wave, you have to replace this access point anyway. They don't have millimeter wave modules.
Is it just one device or is it an array of these light LEDs?
So we tried both. Of course, having more than one light source can give you diversity and is helpful, of course. But again, in the light, the photodiodes and also the light source, they're not that expensive comparing to millimeter wave module itself. So if they want to replace the access point and put a more expensive access point that has millimeter wave, I don't think they kind of bother putting a better sort of LED, which is a few bucks more expensive. So comparing to that. On your second question, I totally agree. Actually, the benefit of using this interference cancellation on the analog domain is one of the things that you mentioned. If we want to cancel the interference in the digital domain, means that we have to find the amplitude and phase from all the antenna at the transmitter to all the antenna at the receiver, or basically measuring the CSI, then a small movement of the device can actually, or the environment, can change the phase at our antenna. So CSI can completely change. Like in communication, if you change by half a wavelength, it's a completely different CSI, right? And half a wavelength is millimeter here, right? 2.5 millimeter. But if you look at this problem in the analog domain and just follow the path, so if you have a line of sight path and you move, you don't, and then it is not just one ray, it's a cluster of paths that you model with single path, right? So that path characteristics doesn't change a lot. And we are not relying on phase here. We are mostly relying on amplitude of the signal. So that's why if you do this on the outdoor actually, or even in a dynamic scenario indoor, it's more promising for mute. Comparing to the traditional way of handling interference. Also, as we go outdoor, we expect to see channels to be more line of sight dominant than basically reflection dominant. So we will be actually, at the end of the day, kind of rely on the line of sight itself to transmit to multiple streams. So it's a great question, and we haven't done it. That's just my expectations to see outdoors.
Yeah.
So in your Modicon paper from the mute algorithm, you mentioned that it will be required to do it in the IP because normally it has more resources. Mm-hmm. And having worked with commercial off-the-shelf devices, it makes me wonder how much CPU intensive is your mute algorithm compared with the baseline, since you only have a very limited time space to do these calculations. Mm-hmm. Have you done anything?
It's not necessarily needs to be done at the access point, but the thing that we didn't talk about in that paper is how that feedback link should look like if we want to do it on the client device. So that's basically a MAC layer design on how, now that we have this information locally at client, how we can kind of send it back to the access points, or how we can send, like, what portion of the data that we measure at the client, how can kind of compress that, and what are the most kind of key components to send to the access point to let the access point actually handle the situation and again find the right beam. So those sort of things, we haven't looked into that, but for sure will be considered in future work.
Let me ask you, your method, just to clarify, you're working at 60 gigahertz. Is it fair to say the methods that you presented, whether LIST or mute, you really rely on mostly specular reflections and a few paths, right? So unlike at 2.4 of these 5 gigahertz where you have a lot of diffuse, multipath, rich scattering, that's not where this is supposed to work well.
No.
Okay, so that's the first
Exactly.
point, right?
So that's like when we have a sparse path, and also we have this wide bandwidth so that we can distinguish between different paths.
Sure. The other point is, this is to continue something that Chris asked, that when you have either outdoors or a high mobility scenario, and you're still working within the 1180 beam steering, beam searching framework, that seems like a hard problem to solve, right?
Yes.
So there has to be some breakthrough, because using the same old method and you're not stressing the problem space. So one thing I didn't see you discuss is that the reason to have all these multiple streams is, of course, to increase the data rate simultaneously.
Yeah.
But then in all of these difficult scenarios, there's always a component of user selection. You don't have to send everything at every time to people. So is that going to be incorporated in your?
It was in one of the publications I referred you to, but I didn't talk about it through this, of course. So I talked about user selection and the coupling between user selection and beams. So basically, if, let's say, you have a primary user and the secondary user that you want to select with that primary user changes, your beam, the best beam configuration may completely be different. So the overall kind of optimization framework that we want to avoid doing is joint user and beam selection. So that's why we want to kind of decouple these two problems because that's a practical way of thinking about that. And I've done some kind of work in my PhD to address that problem too.
Oh, yeah, sure.
So you said that the exhaustive search has complexity order n to the s.
Yeah.
Do you have an estimate of what the complexity is for your algorithm?
For mute?
Yeah.
Yeah, so because mute is repurposing something that is already there in the 11AD and 11AY, it's basically the complexity is not that much. It's basically just we down select the sort of, I haven't talked about it. Based on mute, we down select like a few beams that the number of beams is in the order of number of multipass component that you have in the channel, which is like in average 2, 3, 4. So we down select based on that, and we do a local training on these beams only to find the right configuration. So that's why it's order of my mute basically is order of number of multipath component, whereas exhaustive is order of n to the power of s. Even if you consider that periodic sweep as like part of mute's overhead, still that is order of n, which is number of beams that you have, still linear.
So it seems like you're doing some coarse sampling. Is it possible to get a finer beam after you do the coarse sampling?
Yes. Yes, so basically that's even like the next generation IEEE Yasaman 11AY actually kind of has mechanisms to allow for that. So there's a kind of training mechanism for that goes over basically a down-selected set of beams. So here I'm talking about how we can down-select and have that subset of beams, but there are mechanisms for how to find the right configuration out of that down-selected subset of beams.
So following up on that, there is so you're assuming that the receiver has an isotropic pattern?
No. It's like whatever it has, it's fixed.
But maybe after the transmit beam is fixed, then the receiver beam can adapt to...
So I didn't talk about it actually, it's a great question. So we kind of envision that access points and client, because there's like two-phase sweep, right? So on one phase, one subset of beams can be selected, on the other sweep, the other side, you know? So, and then at that kind of local training phase, which I didn't talk about, now because of the fact that we did these two selections independently, we actually can now find the right configuration that works best comparing these two together. So, great question.
But just a side question in this is that there does not seem to have been, and I'm curious to know why, much work at all on coding, looking at beam, coding in this beam search. Do you know why? Because clearly, these complexity bounds you're providing are for exhaustive search, one way or the other. And of course, there's all this information that has to be sent back and forth. But why hasn't beam space coding, been looked at more?
I think, I don't know. I mean, I think I have seen like initial efforts on that, but it's not really developed.
So I think that's part of the answer.
Yeah.
Okay. Any further questions? If not, let's thank the speaker once again.